Hello dear students. So today we will discuss the absolute value and its properties. Absolute value of a real number, okay, or this is also called modulus of a real number. Okay. So what is that? You have seen in your school days also. What is mod of -2? It's 2. Okay, so it gives us the positive value, right? Non-negative value. Mod of 0 is 0, right? Mod of 3 is 3. So if the number is itself positive, then the mod is itself, okay. And if the number is negative, then the mod is minus of that number. Okay, this 2 is actually minus of -2. Okay, so this is the definition. So let us see how it is defined. So the absolute value of real number x is denoted by mod x. Okay, this mod x, and is defined as mod x equal to set of x, means x when x is greater than 0, 0 when x is equal to 0, and minus x when x is less than 0. It means if x is positive, then mod x is x itself. If x is 0, then it is 0, and if x is negative, then we know minus x is positive, so minus x gives you the modulus of this, right? So this is the definition. So using this definition, we will prove some properties. Okay, so by definition, some properties easily follow by definition. But so by definition, you see whatever value we have taken for mod x, each value is non-negative. When x is greater than 0, this mod x is x, right? So that is also greater than 0. 0 is also greater than or equal to 0. Minus x is also greater than 0, right? So by definition, mod of x, this is always greater than or equal to 0 for all x inside R. Okay, right? Modulus of a real number is always non-negative. Okay. Another property that follows is mod x. See, the value of mod x is 0 in only one case, when x equal to 0. Okay, so mod of x equal to 0 if and only if. Okay, if and only if x equal to 0. Okay, so the meaning is, if mod x is 0, then x has to be 0, and the other way, if x is 0, then mod x has to be 0, right? So this is a if and only if type. So mod x is 0 if and only if x equal to 0, right? Then we have mod of minus x is same as mod x. Okay, mod of minus x is what? By if we apply definition, it is minus x if minus x is greater than 0, 0 if minus x is equal to 0, and minus of minus x if this minus x is less than 0. Okay, so I can write it this way. This is same as minus x if minus x greater than 0 means what? X is less than 0. Okay, and 0 if minus x equal to 0 means x is 0. Okay, and this is minus of minus x means x when minus x less than 0 means x is greater than 0. So this is nothing but mod x only. So mod of minus x is same as mod x. Okay, so something like mod of minus 3, this is same as mod 3. Okay, which is equal to 3, like that. So these are some important properties of modulus which follow directly from the definition. Okay, then there are other properties also. Let us do it as a theorem. We can write it this way: number A or number 1. Number 1 is modulus of AB is equal to mod A multiplied with mod B for all A, B inside the set of real numbers. Okay. So we can separate the product. Okay, mod of the product is equal to product of the mod. Okay. Number 2 is mod A whole square is same as mod of a square. Okay, so it will follow from the first one for all a inside R. Number 3 is if c is greater than or equal to 0, then mod a is less than or equal to c if and only if minus c less than or equal to a less than or equal to c. Okay. So this property we will always use. If we have something like mod x is less than or equal to 5, this actually means that x lies between minus 5 and plus 5. Okay. So this is what we'll prove. Number 4 is minus of mod a is less than or equal to a less than or equal to mod a for all a inside R. Any real number lies between these two values, minus of mod a to plus of mod a. Okay. Means actually it is any real number is either equal to minus mod a or plus mod a. Okay. In general we can write it this way. So let us try to prove this. So for the first one, we see if a and b are both 0, okay, or if one of them is 0, if a equal to 0 or b equal to 0, then ab equal to 0. Okay. So mod of ab is equal to 0. Also in this case mod of a is equal to 0 or mod of b equal to 0. So any one of them is 0. So mod a mod b also equal to 0. Thus mod of ab is same as mod a mod b if one of them is 0. Okay. If one of them is 0. Okay. So let us assume that none of them are 0. So let a not equal to 0 and b not equal to 0. Okay. So there are several cases by law of trichotomy. So a can be greater than 0 or b can be greater than 0. Another case is a greater than 0, b is less than 0. Okay. Another case is a less than 0, b less than 0. And another case is both are less than 0. So we have to deal with these cases separately, right? Okay. So if a greater than 0 and b is also greater than 0, then by order property, what do you write? We have this a b is also greater than 0. So therefore and mod of a is equal to a, right? Mod of b equal to b. Okay. And mod of ab is equal to ab. So therefore mod of ab equal to so let me write it in the next line. Therefore mod of ab is equal to ab. Why it is ab? Because ab is greater than 0 by definition. Okay, so this follows by definition. But this a I can write it as mod a, b I can write it as mod b. So mod of ab is same as mod a mod b, right? If a is greater than 0 and b is less than 0, okay, a is positive, b is negative, then so by order property or by a consequence of order property. So earlier one was direct application of order property. Here it is by a consequence of order property. Means we have to go one step forward. Since b is negative, so minus b is positive. Okay, so by a consequence of order property, a into b has to be negative. Okay, a into b is less than 0. And so mod of ab, so by definition mod of ab will be minus of ab. Okay, minus of ab. But I have a is greater than 0, so this can be written as a into minus b. Okay, so by field properties, so this is A is mod A and B minus B is actually mod B. Okay, since B is less than 0, so mod of B is same as minus B. So we replace this minus B by mod B. So mod of AB is mod A mod B, we have already proved. Okay, the other case is similar. Similarly, if A is negative, if A is less than 0 and B is greater than 0, okay, then mod of AB, this is same as mod A mod B. Okay, this is this. Now let if A is less than 0 and B is less than 0, okay, both are less than 0, then the product AB is greater than 0. Therefore, mod of AB, this is equal to AB only. But I can write this one as minus A into minus B, okay, by field properties. Right, so minus A is again, this minus A can be written as mod A and minus B can be written as mod B because A and B are less than 0. Okay, so thus in all cases, mod of AB is same as mod A multiplied with mod B. Okay, both are equal. Okay. Next, what is the thing? I have to show that mod A whole square is same as mod of S square. Okay. So that also we can use this fact that number 2. So given any A inside R, we have A square is always greater than or equal to 0. Hence, mod of S square is equal to what? Equal to S square only, right? Mod of S square is same as S square. Now I have to show that this S square can be written as mod A whole square. So there are two cases. Okay, if A is equal to 0, then both sides are equal. Okay, then mod A is also equal to 0, and so mod of A square is same as mod A whole square. Okay, if A is greater than 0, then A is equal to mod A. So mod of A square is same as A square, which is equal to A into A, but A can be written as mod A, so it's mod A into mod A, so that is mod A square. Okay, if A is less than 0, then this mod A is equal to or minus A, that is A equal to minus of mod A. Okay, so mod of A square is actually equal to A into A. This is always true for this one. So this A can be written as minus of mod A multiplied with again minus of mod A. Okay, so minus of mod A into minus of mod A, that is actually mod A square. Okay, so we have proved for all cases, right? Yeah. Yeah, so we can do it this way, or we can just use the earlier property. Okay, so let us do it independently. We have shown. So in exam it might happen that you are given only this one, so then you cannot write that from the earlier example. Okay, so better do it independently. We've done it. Number 3 is what? If C is greater than or equal to 0, then mod A less than or equal to mod C, if and only if C this A lies between minus C and plus C. Okay. Okay. So let us try to show this. Given C is greater than or equal to 0. Okay. And so there are two parts here, if and only if. So first let mod A less than or equal to C. Okay, so if mod A is less than or equal to C, then what we can say? what can we say? Then we have see one thing you can see that minus of mod A, this is always less than or equal to mod A, right? Minus of mod A, this is a negative quantity. Okay. So minus of mod A is actually less than or equal to 0. Okay, because mod A is greater than or equal to 0. So minus of mod A is actually less than or equal to 0, right? And then I can write this is less than or equal to mod A. So actually minus of mod A is less than or equal to mod A. Okay, so we can bring minus of mod A somewhere here, right? So let us see how we can do this, or we apply the definition here. Okay, so mod A is less than or equal to C, right? So if A is greater than 0, then mod A is equal to A. Okay, so mod A less than or equal to C implies that A is less than or equal to C. Okay, and if A is less than 0, then mod of A is equal to minus A. Okay, so therefore mod A less than or equal to C implies that minus A is less than equal to C. Okay, so okay, no, we have to do it in a different way. Just let us so first let mod A is less than or equal to C. Okay, so we see another equivalent thing about mod A is equivalently we can write, see, mod A is actually equal to A if A is greater than 0, 0 if A is equal to 0, minus A if A is less than 0. Okay, so mod A, another definition I can write about mod A is it is maximum of, so out of all this, the largest this out of A and minus A, it's the maximum of A comma minus A, right? Say something like mod of minus 2. What is that? It's 2. So it's 2 actually. Okay, so out of all this 2, 0 and minus 2, which one is the mod? The mod is actually 2. Okay, so it is the largest out of all this 2. Okay, that's obvious because we are taking only the positive one, right? So mod A is actually the maximum of A comma minus A, right? So that is another equivalent definition of modulus of A. Okay, so we can use it here. So first let mod A less than or equal to C. We have mod A equal to maximum of, so for A equal to 0 also this definition is okay, because if A is 0 then it's maximum of 0 comma 0, so that is 0 only. Okay. If A is minus 2, then it is maximum of minus 2 and 2, so that is 2. Okay, so we have mod A equal to maximum of A comma minus A. So now you see that mod A is less than or equal to C and mod A is maximum of this 2. Okay, so we have something like maximum out of A comma minus A is less than or equal to C. That means both of them are less than or equal to C. Okay, so thus maximum of A comma minus A, this is less than or equal to C. So this implies A is less than or equal to C and minus A is also less than or equal to C. Okay, both have to be, because the largest of them is less than or equal to C. So both of them have to be less than or equal to C. Okay, right. So A we have, so this implies A is less than or equal to C and minus A is less than or equal to C. So this can be written as okay, so I just add another line that yeah, so this is A less than or equal to C, and so if I just multiply with negative minus 1, then the inequality will get reversed. We have already seen. So a greater than or equal to minus c. Okay. So this implies, so this can be written as what? Minus c is less than or equal to a, and a is less than or equal to c. So a lies between minus c and plus c. Okay. So this is already there. So we have proved this part, right? So if c greater than or equal to 0, then mod a less than or equal to c implies this happens. Okay. Now the other part we have to prove. Conversely, if minus c less than or equal to a less than or equal to c, then modulus of a is actually less than or equal to mod c. So let us see. Conversely, let minus a less than or equal minus c less than or equal to a less than or equal to c. Okay, so this implies what? Minus c is less than or equal to a, and a is less than or equal to c. Okay, so this implies if I multiply with minus again here, so it's just getting reverse. Okay, so c greater than or equal to minus a, and a is less than or equal to c. So I can write this as c greater than or equal to minus a. I can write as minus a is less than or equal to c, and a is less than or equal to c. Okay, so this way, and from there I can write it as you see both of these quantities a and minus a, they are less than or equal to c. So maximum of the largest of them is also less than or equal to c. Okay, so maximum of a comma minus a is same as mod a. Mod a is less than or equal to c. Okay, right? So we have proved both the parts, right? Okay. Okay. Right. So the other one, another property that we had listed is a lies between minus mod a and plus mod a. Okay. So how do you show this? So we can show it easily by taking c equal to mod a here. Okay, in this earlier problem. Okay, or we can do it independently as this. So we have, so just we'll use this definition. Mod a is same as maximum of a comma minus a. Okay. So a is less than or equal to mod a. So maximum of a and minus a is mod a. So that means both of them are less than or equal to mod a. Okay, so a is less than or equal to mod a, and minus a is also less than or equal to mod a. So this implies a is less than or equal to mod a, and I multiply both sides by minus 1, so it's a greater than or equal to minus mod a. Okay, so this can be written as minus mod a is less than or equal to a less than or equal to mod a. Okay, so this is what we have proved. Okay, so proved. So this is also very important, right? This one and the earlier one, that this one is c greater than or equal to 0, then mod a less than or equal to c if and only if a lies between minus c and plus c. Okay, so if we have something like mod of x plus 2 less than or equal to 5. Okay, so immediately in the next step we can write minus 5 less than or equal to x plus 2 less than or equal to 5. Okay, and then just shift the side. So minus 7 less than or equal to x less than or equal to 3. Okay, so if mod of x plus 2 is less than or equal to 5, then x lies between minus 7 and 3. Okay, so in analysis very often we will come across this type of things. A mod of xn minus L is less than epsilon. So what does this mean? This means that xn minus L, this lies between minus epsilon and plus epsilon. Okay, so that is the thing. So that is L minus epsilon is less than xn less than L plus epsilon. Okay, so this is these things will be regularly used in your analysis. Okay. Okay. Another very important property is the triangle inequality, and this is the theorem. This is the triangle inequality. Okay, so what is that? The triangle inequality is mod of x plus y. This is always less than or equal to mod x plus mod y. Okay, for all x, y inside real number. Okay, so why it is called triangle inequality? So it's something like sum of two sides is, these are the sum of two sides. So the sum of two sides is greater than or equal to the third side. Okay, so if you have two sides of a triangle which are denoted by x and y, okay, so something like this. If two sides are denoted by x, in vectors you have done, so if two sides are denoted by this x vector, y vector, then the sum is denoted in the opposite direction by x plus y. Okay, so sum of mod x represents this length, mod y represents this length, sum of two sides is greater than the third side. Okay, so that is why it's actually called triangle inequality. Okay. So this is also one of the most important results that we will be using in almost every step of real analysis. Okay. So triangle inequality, so let us try to prove it. Okay. So we have minus mod x is less than or equal to x less than or equal to mod x. Okay, this just now we have proved. And minus mod y, this is less than or equal to y, this is less than or equal to mod y. Okay, x lies between minus mod x and plus mod x, y lies between minus mod y and plus mod y. So we can add this to, in our properties of inequality we had already done, if a is greater than b, c is greater than d, then a plus c is greater than b plus d. Okay, so this property already we had done almost, I think, yeah, we had done this, it was listed here also. Yes, if a greater than b and c greater than d, did we do it? If we didn't do also, means it's simple, we can do it quickly. It was listed as an exercise or what? If a is less than c, b is, yeah, I think I had given you it as an exercise. So just let us quickly recall. If a less than b and c is less than d, okay, then we can just add them. A plus c is less than b plus d. Okay, so how to show this? A less than b means what? B minus a is greater than 0. Okay. C less than d means d minus c is greater than 0. Okay, so their sum is also greater than 0 by order property. So b minus a plus d minus c, this is also greater than 0. Right? Okay, so it's recording. Where is it? Okay, so b minus a plus d minus c is greater than 0. So from here we can see that b plus d minus of a plus c, this is greater than 0. So from that, by definition it follows that a plus c is strictly less than b plus d. Okay, so basically this property we will use. Okay, so if we add this two, we get adding we get something like minus of mod x plus minus of mod y. This is less than or equal to x plus y. This is less than or equal to mod x plus mod y. Okay, and then if I take this minus common, so it's minus of mod x plus mod y is less than or equal to x plus y less than or equal to mod x plus mod y. Okay, so x plus y lies between minus of this to plus of this. Okay, so whenever we have this type of thing, so I can use that minus c less than or equal to a less than or equal to c. This actually means that mod a is less than or equal to c. Okay, of course this c has to be positive. Okay, so here you see C has to be non-negative. So here you see these are non-negative quantity, right? So from this line actually I can write, this implies mod of x plus y, this is less than or equal to mod x plus mod y. Okay, so it's just properties of inequality. Okay. X lies between minus mod x and plus mod x, y lies between minus mod y and plus mod y. Just add them, we get minus of mod of x plus y, minus of mod x plus mod y is less than or equal to x plus y, which is less than or equal to mod x plus mod y. Okay, so that is the thing. So from there itself it follows that mod of x plus y is less than or equal to mod x plus mod y. Okay, so it's a very important property. Okay. Okay, so there are some corollaries for this result. Corollary means a result which follows from another result by some simple steps. Okay, so number one is, if we have mod of this one, mod of mod x minus mod y. Okay, consider mod x minus mod y and then again take mod, this is less than or equal to mod of x minus y. Okay, for all xy inside R. And another one is number 2, mod of x minus y, this is I should have done first this one, mod of the number b is actually straightforward. Let us do b first. So number 1, mod of x minus y, this is also less than or equal to mod x plus mod y. Okay, for all x y inside R, right? Number 2 is mod of mod x minus mod y, this is less than or equal to mod of x minus y. Okay, for all x y inside R. Okay, or this can be actually equivalently written as what, mod x minus mod y, that is also less than equal to mod of x minus y. Okay, not equivalently means there are two parts actually. Mod x minus mod y is less than or equal to mod of x minus y, as well as mod y minus mod x is also less than or equal to mod of x minus y. Okay, so we'll write it. So solution is, for the first one it's very simple, mod of x minus y, this is equal to mod of x plus minus y. Okay, we can write it as this, x plus minus y, and then apply triangle inequality, this is less than or equal to mod x plus mod of minus y. And in the beginning itself we have seen the definition, from the definition it follows that mod of minus y is same as mod of y. Okay, since mod of minus y is equal to mod of y. Okay, so you might be wondering why I have written this equal to here. Okay, why not less than or equal to? So actually from this step to this step it's an equality. Okay, because mod of minus y is same as mod of y. Okay, so when I write equal to here, it means that this step is actually equal to this step. Okay, it doesn't mean that this is equal to the original one. Original one is already less than this. Okay, this quantity, but this quantity is equal to this. So ultimately mod of x minus y is less than or equal to mod x plus mod y. Okay, so from here, therefore mod of x minus y is ultimately less than or equal to mod x plus mod y. Okay, so this part already we have proved. The second part is we have to deal with mod of x minus y. So how to deal with this, the second one. So you see, if I start with something like this, mod of x minus y, in that case I will just get it is less than or equal to mod x plus mod y. Okay, so it's not helping me out. Let us start with mod x. We have mod of x is equal to mod of, instead of x I can write x minus y plus y. Okay, I can write it this way. So this is less than or equal to mod of x minus y plus mod y. Here I have applied triangular inequality, okay, on this one, mod on this x minus y and y. So this follows by triangle inequality. Okay, and then I can just change sides. So this implies mod x minus mod y. This is less than or equal to mod of x minus y. Okay, so one part I have shown. See, if I can show that this some quantity z is less than or equal to mod of this, okay, whatever it is, and some quantity minus z is also less than or equal to this same quantity. Say I write a. If I can show that z is also less than or equal to a, minus z is also less than or equal to a. Okay, in that case I can write maximum of z comma minus z is less than or equal to a. Okay, so it will follow that the modulus of z is actually less than or equal to a. So this is what I am planning here. So here you may keep it as 1, and also, so I'll apply the same thing with y. So mod of y is actually mod of y minus x plus x. Okay, so I can write it, this one is less than or equal to mod of y minus x plus mod x. Okay, but y minus x modulus is same as mod of x minus y plus mod x. Okay, so therefore mod of y minus mod of x is ultimately less than or equal to mod of x minus y. That is minus of mod x minus mod y. This is less than or equal to mod of x minus y. Okay, so this is 2. So from 1 and 2 it follows that this modulus of this quantity is actually less than or equal to, or let me do it one more step so that it's easier to understand. So here this implies if I multiply both sides with minus 1, so it's mod of x minus mod of y. This is greater than or equal to minus of mod of x minus y. Okay, so from 1 and 2 what we can write. Okay, or yeah, let us do it. Yeah, okay, let us do it this way. I'll show you the other way also. So from 1 and 2 we can write minus of mod of x minus y. This is less than or equal to mod x minus mod y, and this is also less than or equal to mod of x minus y. Okay, so this actually means that so we have something similar to this, minus c less than or equal to a less than or equal to c. So from there I can always write mod a is less than or equal to c. Okay, so from this it follows mod of mod x minus mod y, this is less than or equal to mod of x minus y. Okay, right, or else you can do it this way, or else, so we have by 1 we have mod x minus mod y is less than or equal to mod of x minus y, and by 2 we have minus of this mod x minus mod y, this is less than or equal to mod of x minus y. Okay, so therefore maximum of mod x minus mod y comma minus of mod x minus mod y, this is less than or equal to mod of x minus y. Okay, but what is this? This is nothing but mod of mod x minus mod y. Maximum of a comma minus a is mod of a. Okay, so this is less than or equal to mod of x minus y. So we can do it this way also. Okay, both are okay. Right, so if you are getting confused with maximum of this too, okay, I think this is more clear. Means it's in many of the cases this is also helpful. Okay, so we can do it in any of the methods. So these are the properties of modulus we have done. Let me just see whether there are other. Okay, so there are a few more properties which we can do. Means one corollary which follows. Okay, another corollary, it's a generalization of the triangular inequality. Okay, so if a1 a2 or say x1 x2 up to xn belongs to real number, then mod of x1 plus x2 plus dot 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 up to xn, this is always less than or equal to mod x1 plus mod x2 plus dot 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 up to mod xn. Okay. So it follows by mathematical induction. So we can prove it very easily using mathematical induction. Okay. So we have mod of x1. This is less than or equal to mod of x1. Okay. This is always true, right? Because mod of x1 is actually equal to x1. So less than or equal to x1, that is also true. Okay. So for n equal to 1, the result holds and the result is true. True. Okay. So for n equal to 2 also it's true by this triangle inequality. Okay. So let us assume that it is true for n equal to k, right? Let us assume that mod of the result is true for the result is true for n equal to k. Okay. Right? Where k belongs to natural number. Okay, belongs to natural number. That is, we are already given that x1 plus x2 plus up to xk. This is less than or equal to mod of x1 plus mod of x2 up to mod of xk. Okay, this is already given to us. So we can apply or we can so this is already given to us. Okay, here actually we need to use the this triangle inequality somewhere. Okay, so for n equal to 2 also, I'll just state here, for n equal to 2 we have triangle inequality gives triangle inequality. So since we have written it as a corollary, we have to use it somewhere here. Okay, triangle inequality gives mod of x1 plus x2. This is less than or equal to mod x1 plus mod x2. Okay, this is given by triangle inequality. So next we will suppose that this is true for some k. Okay, then mod of x1 plus x2 plus dot 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 up to xk plus we add another one. Okay, and see whether the result is true or not. So this can be written as x1 plus x2 plus. So what I have to use here, I have to use something called the associative property of this field axioms. Okay, see, I have used the associative property here. So I have grouped this together and then I have separated this. So this can be written as less than or equal to mod of x1 plus x2 plus up to xk plus mod of xk plus 1. Okay. So this follows by triangle inequality. Okay. Triangle inequality. And this is less than or equal to mod x1 plus mod x2 plus dot 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 up to mod xk, okay, plus mod of xk plus 1. So this is not by triangle inequality, this is by in the induction hypothesis. Okay, by induction hypothesis. Okay, so you have to understand these steps clearly. This one, the earlier step we have got by triangle inequality, because this is one real number, this is another real number. We have proved the triangle inequality for two real numbers. Okay, so using the triangle inequality for two real numbers, we have got this. Next, for k real numbers we have not proved. We have assumed the induction hypothesis that this is true for k, n equal to some k. Why our hypothesis is means why we can choose that hypothesis, because at least it is true for a k equal to 2. Okay. So say if k equal to 2, then we prove it for k equal to this n equal to 2 plus 1, that is 3. Okay, so that way the induction proceeds, right? So here from this step to this step we have come to this step because of induction hypothesis. Okay, so ultimately we have proved it. Thus the result is true for n equal to k plus 1. Okay, so by principle of mathematical induction the result is true for any n belongs to natural number. Okay, so if you take any n real numbers, then the modulus of their sum is less than or equal to the sum of their moduli. Okay, so the plural of modulus is moduli. Okay, that is the thing. So this one we have already proved. Say another exercise: determine the set A equal to set of all those real numbers which satisfy twice x plus 3 modulus equal to less than 7. Okay, so how do you determine this? So the solution, so you can just start with A equal to set of x belongs to R such that mod of twice x plus 3 is less than 7. Okay, so this is the set of x being R such that minus 7 is less than twice x plus 3 less than 7. Okay, this is the set. So this is the set of all those real numbers which satisfy this condition. So you take minus 3 to this side, so it's minus 10 less than twice x less than 4. Okay, so what I have done, I have taken 3 to this side. Okay, I have taken 3 to this side. So there are two inequalities actually: minus 7 less than twice x plus 3 and twice x plus 3 is less than 7. Okay, so from the first one I get this, from the second one I get this, and using the AND connective I can write it this way. Okay, so this is x belongs to R such that now we can divide, means we can multiply by half. Okay, so that's division by 2. Okay, so if you divide this, then you get minus 5 is less than x less than 4. Okay, so this is this set. It is the set of all those real numbers which lie between minus 5 and 4. Okay, sorry, minus 5 and 2. Okay. 4 divided by 2. Okay, so this set is actually written as an interval, even though I have not done this part now. So till from your higher secondary knowledge itself, you know, and this is the set of all those real numbers which lie between minus 5 and 2 is actually open interval minus 5 comma 2. Okay, so this is called an open interval. Okay, this one. Next is say suppose I want something like determine the set exercise. Determine the set A equal to mod of x belongs to R such that mod of x minus 1 is strictly less than mod x. Okay, mod of x minus 1 is strictly less than mod x. Okay, so here it's a little bit complicated, so let us just avoid writing it in set form. Okay, so we have mod of x minus 1 is strictly less than mod x. Okay, so this means that what? This means that minus mod x is less than x minus 1 less than mod x. Okay, so this is the one. Okay, but we have to deal with this mod, right? So it's better to separate it into 3 cases. Okay, so if x is 0, what happens? If x equal to 0, then we have this is the left hand side here will be mod of 0 minus 1 is equal to 1. Okay, mod of 1, but mod of x, if x equal to 0, then mod of x minus 1 is actually 0 minus 1, so there is 1, but mod of x is 0, so, but 1 is not less than 0. Okay, but mod of x equal to 0, so the inequality is not satisfied. Okay, inequality doesn't hold. Okay, as for x equal to 0, mod of x minus 1 is 1. Okay, but we cannot write 1 is less than 0. Okay, because 1 is already greater than 0. So for x equal to 0, it doesn't hold. Okay, so let x be say less than 0. Let us consider the less than 0 case. Then your mod x is same as minus x. Okay, so if we have this, so mod of x minus 1 less than mod x will implies that this minus mod x is less than mod of x minus 1, x minus 1, this is less than mod x. Okay, but x is negative, so mod x is actually minus x, so it's minus of minus x. This is less than x minus 1, this is less than minus x. Okay, so this implies x is less than x minus 1 and x minus 1 is less than minus x. Okay, so let us separate this. So x is less than 1, this actually means that 0 is less than minus 1, which is not true. Okay, so let us write it this way. But so here you have AND connective, so this statement, the connected statement, will be true if both of them are true. Okay, but here you see, but x less than x minus 1 is not possible, as this gives 0 is less than minus 1. Okay, so that is incorrect. Okay, so this case is itself, so x cannot be less than 0, thus x less than 0 is not possible. Okay, is not possible. Okay, so we are left with only one case, let x greater than 0, then mod of x minus 1 less than mod x will imply that minus mod x is less than mod of x minus 1. Again I have written mod. If I split the mod, then I get something like minus of mod x is less than x minus 1 less than x mod x. Okay, but mod x is x. If x greater than 0, then this is happening. So mod x is x only, so it's minus x less than x minus 1, minus x less than x minus 1 less than x. Okay, so this actually means minus x is less than x minus 1 and x minus 1 is less than x. Okay, so from the first one you see you get something like if you just change the sides, it's twice x is greater than 1, and here you from this one you get something like x minus 1 is less than x. Okay, this is always true for all real numbers. Okay, this part it is always true. Okay, and this part is true under some condition. Okay, so so this implies actually, so if I just change the sides, it's twice x minus 1 is greater than 0 and x minus 1 is less than x. Okay, so x minus 1 is less than x means minus 1 is less than 0. Okay, so this part is always true, which is true, right? So both of them are true, both of them will be true if this happens. So if x is greater than half, okay, x greater than half and minus 1 is less than 0. So since this part is always true, so the truth of this statement depends only on this part. Okay, x greater than half, so that is x is greater than half. Okay, no value of x from case 3 satisfies from forming the union of this case. This is yeah, so in case 2 the inequality becomes this, which requires x is greater than half. Thus this contributes all x to the set. Okay, Yeah, so this x greater than half and minus 1 less than 0. So we can, since minus 1 less than 0 is always true, okay, but minus 1 less than 0 is always true, okay, always true. So it follows that this x is strictly greater than half. Okay, so the required set is, the required set is A equal to set of all those x in R which satisfy x is greater than half. Okay, all other cases are invalid. If x less than 0, then also it's not satisfying. If x equal to 0, then also it doesn't satisfy. And if x greater than 0, it is satisfied only when x is greater than half. Okay, because this inequality will imply this one, x is greater than half. Okay, right. So this is the required set. Okay, so in the next class we'll do a few more things about in the next class we'll start this that is called supremum, infimum, least upper bound, greatest lower bound. Okay, bounded sets and all. Okay, and we'll do something about neighborhood. So before that I'll give you some homeworks you may try. Okay, I'll give it to you in the Google Classroom so that you can try those homeworks. Okay, thank you.